All right, so we're going to talk about some different situations, a lot of mathematical situations that involve energy. Some we'll do in the board, some we can do verbally, but we'll discuss. So, first off, as we relate work to energy, remember your initial mechanical energy plus work, either added or subtracted, will then equal your final kinetic energy or your final mechanical energy. Just understand that these two added together do not equal these two. There's going to be work involved. This could be less or this could be more on the left side than on the right side when we talk about kinetic and potential energy being, or the mechanical energy being conserved, okay? So remember, mechanical energy not conserved when we have work. So we're raising a barbell vertically. So we got a weightlifter applies an upwards force, let's say 1,000 newtons, to a barbell to displace it 0.25 meters at a constant speed. So initial energy is 1,500 joules. So our initial mechanical energy, 1,500 joules. That's here. The work is the force we apply, which is 1,000, times the distance we move the barbell, 0.25, times the cosine of 0, which is 1 because it's all in the same plane. So it's 1,000 times 0.25, which equals 250. So if we take our initial mechanical energy of 1,500 plus the 250 joules of work that the weightlifter does, we get a final mechanical energy of 1,750 joules. Okay, so total mechanical energy initially is different than final because of the work that we have done to the barbell. Another situation, we got a baseball catcher who's applying a force to the right when the baseball is moving left towards it. Okay, so we're trying to stop the baseball by applying a force to it. So here's where the catcher's mitt starts. When it catches the ball, here's where it stops. The force is, by the catcher, 6,000 newtons, and the distance is 0.1 meters. So again, we're on a flat surface, so my angle is going to be 180 because I'm going this way, which is -1. So this times -1 equals -600 joules. So we do that much work. So initial energy of the ball, 605 joules. So our total mechanical energy initially is 605. We do negative work of 600, which means our final total mechanical energy is going to be 5 joules. So 5 joules of total mechanical energy at the end. Again, total energy is conserved, but total mechanical energy is not because work is being done. A skidding car. So we got a car going from a high speed to a low speed. We got friction of 8,000 newtons. And while we hit the brakes, it goes about 30 meters as we hit the brakes from starting here to starting here. So what's the final energy of our car? So our total mechanical energy at the beginning is 220,000 joules. The work is our force times distance. Force times distance times cosine of 180 because this is 180 degrees. So it's going to be -1. We're going to be doing negative work, and we get negative 240,000 joules. So that's our work. So 320 minus 240,000 gives us final mechanical energy of 8,000 joules. So the car has lost energy due to friction, okay? And that work, or the friction, was what the work that was done on the car. Like what we did in the in class with the interactive, pulling the cart up the incline. When we look at this, so we got initial energy 0. When we pull it to the top, what is the final energy? So we're at the bottom, no initial energy. We apply a force of 18 newtons over 0.7 meters. So if we go 0.7 meters and 18 newtons, and it's all on a plane, so our angle's 0, 18 times 0.7 times cosine of 0, which is 1, equals 12.6 joules. So we do 12.6 joules of work. The energy at the top then is 12.6 joules. So we give energy to the cart by doing work on it because we do positive work. All right. So that's how we look at that equation and how we can solve some things. Now we're going to do a couple on the board here. We got a 1,000-kilogram car traveling with the speed of 25 meters per second, skids to a stop. The car experiences an 8,000 Newton force of friction, determining the stopping distance of the car. So we're trying to find the stopping distance. And there's our information. Do it now. All right. So we got a car. This mass, this velocity, with this much force pushing against it, comes to a stop on a flat surface. And we want to know the distance that it traveled. So let's go total
mechanical energy initial plus work equals total mechanical energy final. So let's look at this. So total mechanical energy initial. So that's potential plus kinetic. We're on a flat surface, there's no potential energy, but there is kinetic. So the kinetic energy here, right, the kinetic energy here is 1/2 mass times velocity squared. So I will calculate that up. Give me a second here. There we go. So we got 0.5 times 1,000 times 25 squared. And I have kinetic energy of 312,500. So that's my total kinetic and total mechanical energy. All right. Work is going to be force times distance. So I'm going to solve for that in a second, and that's going to equal my total mechanical energy final. My final total mechanical energy, since I'm not moving, there's no kinetic energy, and since I'm on a flat surface, there's no potential. That's going to be 0. So I'm going to bring this over, so I'm going to subtract 312,500 from each side. The amount of work that the brakes are doing is negative 312,500 joules. So that's how much work's being done. But we want to find distance. Work is equal to force times distance, right? So my work is this, right? Is equal to my force, which is 8,000 newtons. So negative 8,000 because it's going that way, times my distance, divide by negative 8,000 on both sides. So the distance that my car is going to skid will be 312,500 negative divided by 8,000 negative. Gives me a distance of 39.1 meters. So that's how far the car skidded after it hit the brakes.
We got a shopping cart full of groceries sitting on the top of a hill. It begins to roll until it hits a stump at the bottom of the hill. Upon impact, a 0.25 kilogram can of peaches flies horizontally out of the shopping cart and hits a parked car with a force of 500 newtons. How deep a dent is made in the car? Wow. Over what distance does the 5 Newton force act upon the can of peaches before bringing it to a stop? So that's what we're trying to find. So we have this information all here, and here's the picture. Interesting problem. Do it now.
Okay, so we have a cart way up this hill. It's at rest. It's 2 meters above. I made it way bigger than it normally would be. But it goes down. The cart stops when it hits a rock. And when it hits a rock, a can falls off, hits a car with a force of 500 newtons. And we want to know how far it dents into the car. A lot of math to do that, but not impossible. Okay? So again, total mechanical energy that we start with, right, plus will equal the total mechanical energy that we end with plus the work, because it's going to be afterwards. So let's work through this. Total mechanical energy that we start with. So we don't have a velocity, so there's no potential, or no kinetic, but there is potential because we have height. So potential energy is mass, and I gotta find the mass. It says it's, well, we're just talking about the can, so 0.25 kilograms. So the mass of the can is 0.25 kilograms times G times height, which is 2 meters. So math says 0.25 times 9.8 times 2 gives me 4.9 joules of energy at the top. Now, as it comes down, it gets to here, and this is going to be 0 point, right? And there's no velocity, so it has no height or no velocity. So my total mechanical energy final is going to be 0, right? Because there's no potential nor kinetic. But there is work that gets done to the can. So my work is going to equal 4.9 joules. But like before, work is force times distance. So 4.9 is going to be equal to my force of 500 newtons times the distance that it dents. Divide by 500. And this will give me my distance in meters, so it's going to be a small number. I get 0.0098 meters. And if I move this 1, 2, 3, it's 9.8 millimeters. So not much of a dent, but it will be noticeable and make the car owner very angry.
All right, something about stopping distance. Stopping distance will always be equal to the square of the velocity change. So if you set the slow down 10 meters per second, if you square it, right, then it's going to be stopping distance of 100 meters. So your velocity squared will be there, okay? And now we're going to look at when there's no work, when mechanical energy is totally conserved. So we're going to look at these situations. So same equations before, but no work. These are easier. So let's take, we're here skiing and we go up a hill. As we're at the bottom of the hill, we have a lot of kinetic energy and no potential. As we go to the top, we slow down, so kinetic energy goes down, but we go up in height, so potential energy increases. But total energy here equals total energy here. Now we're at the top, where we have lots of potential and little kinetic. As we get to the bottom, our potential goes down, but we speed up, so our kinetic increases. But again, total energy is the same on both sides of the equal sign, because no work is being done. We're going to look at this pendulum example on the board. Do it now.
Okay, so I didn't draw the pendulum, but we have the different energies and then what we need to solve for. So position 1, potential energy 6 joules, kinetic energy 0 joules. The mass, we can make it be whatever we want. In this case, we'll say the mass will be, is 0.25 kilograms of our pendulum, all right? So potential energy is 6 joules. So potential energy is equal to mgh. Potential energy 6, my mass is 0.25, g is 9.8, solve for h. So h is 6 divided by 0.25 divided by 9.8. So h is 2.5 meters. So this is going to be 2.5 meters up at its very top. And as it starts to swing down, potential gets converted to kinetic. So I'll solve potential energy the same way. Potential energy is equal to mgh. Potential energy is 3. M is 0.25. G is 9.8. Solve for h. So I take 3 divided by 0.25 and divided by 9.8, and I get 1.2 meters. So my height is 1.2 meters. And then how fast is it going? Well, it has kinetic energy. So kinetic energy is equal to 1/2 mv squared. So I'm solving for v. That should be k, sorry. Kinetic energy is 3. 1/2 mass is 0.25 v squared. So I'll take 1/2 times 0.25. 3 is equal to 0.125 v squared. Divide by 0.125. So 3 divided by 0.125 is 24. Is equal to v squared. Take the square root of each. So the square root of 24 is 4.9 meters per second. So that's the velocity when it's there. So now let's talk about position 3. It's all the way at the bottom. no potential energy. If it has no potential energy, it has no height. If we want to solve for V, kinetic energy is 1/2 mv squared. Kinetic energy is 6. 1/2, my mass is 0.25, v squared. Again, 1/2 point times 0.25 is 0.125. 6 v squared divided by 0.125. .48 is equal to v squared. I take the square root of 48, and my v is 6.9 meters per second. And then lastly, position 4, if you look, is just like position 1, and since we don't lose any energy in the process, if I'm at 6 joules, my height is going to be exactly the same. And I don't have to do any math because I've already done it here. That's how you solve a pendulum problem.
Here's a roller coaster. So at the very top of the roller coaster, high potential, low kinetic. At the bottom, we got minimum potential, maximum kinetic. And then as we go up this little hill, we get a little bit of potential back, which means our kinetic goes down a little bit, but it's still going pretty fast. But as a coaster loses height, it gains speed. Potential energy is transformed into kinetic. As a coaster gains height, it loses speed. Kinetic energy is transformed into potential energy. But the sum of kinetic plus potential is a constant, like here. So here we have 40,000 joules, all potential at the top of the hill. At the bottom of the hill, it's all kinetic. And then at different loops, we have different levels of potential and kinetic, but when you add them together, they equal the same mechanical energy, 40,000. This little hill here, a little more kinetic than potential, but at the end it still adds up to 40,000. When we're at the floor level, it's all kinetic, but 40,000. Again, another hill added together, 40,000. And then at the end of the ride, before we hit the brakes, we have a kinetic energy of 40,000 joules. But at the end, or in the total, all energy is conserved. So let's look at a ski jumper. At the very top, all potential. As it starts to skate down the runway, potential goes down, kinetic goes up, but added together equals 50,000. When we get to the point right before we hit the ramp, again, still 50,000 total. When we hit the ramp, we take off, and as we gain height, we lose speed, but we gain potential energy, lose kinetic, but at the end, it still adds up to 50,000. And then when we hit the bottom, all of our potential at the top has been converted into kinetic. Again, this is without friction, so no work's being done. Total mechanical energy is conserved. So we're going to do this one on the board. Do it now.
All right, so we got 100 joules of potential energy at the top with no kinetic energy, so we're not moving. And this ball is going to fall one of two ways. It's going to fall straight down, and it's going to work its way down the slope. So let's work this slope first. So I have 100 joules and 0 joules. When I get to here, I have 50 joules of potential. How much kinetic will I have? Well, if I start with 100 and potential is 50, kinetic will have what's left over. So kinetic energy will have 50 joules. Now to find the velocity, kinetic energy, 1/2 m v squared. Kinetic energy is 50. We'll say the mass of our ball, I don't think it ever said, we'll say the mass of the ball is, we'll go 5 kilograms. 1/2 5 v squared. 1/2 of 5 is 2.5 v squared. Divide both sides by 2.5. That one I can't do in my head. But if I take 50 divided by 2.5, I get 20. Guess I could have. V squared, square root of each side, square root of 20 is 4.5 meters per second is the velocity. Now I look over here, so it gets here and then rolls across. Since there's no friction, my potential energy is still 50, which means my kinetic energy is still 50. If my kinetic energy is 50, my velocity is still 4.5. And then as I come all the way down to the bottom, when I get to the bottom, my potential energy is 0 because I have no height. My kinetic energy then will be the full 100 that I want to solve, so let's do it. Kinetic energy, 1/2 mv squared. My kinetic energy is 100. My mass is, what do we say, 5 kilograms, v squared. 100 is 2.5 v squared. 100 divided by 2.5 is 40, is equal to v squared. Square root of both sides. V is square root of 40. And the square root of 40 is 6.3 meters per second. So that's how fast the ball's traveling to the bottom. So let's talk about from the top. So I start here and get to here. When I get to here, its potential energy is now going to be 0. Kinetic energy is going to be 100. If my kinetic energy is 100, it'll travel at 6.3 meters per second. So right before it hits the ground, that's how fast it'll be going. In a frictionless, airless resistance world, that's what will happen. Energy is conserved.
And then we're going to answer some questions here. So, as an object moves from point A to point D, the sum of the potential energy and kinetic energies, and there's no resistance forces, D, remains the same. Potential plus kinetics the same throughout this whole path, okay? Even though one goes down, the other will go up. Same path, the object will have a minimum gravitational potential energy at its lowest point, B. The object's kinetic energy at point C is less than its kinetic energy at points anything above it, okay? I'm sorry, wait, it says the kinetic energy is at point C is less than its kinetic energy at point. It's less than anything above it, yeah. So the kinetic energies at D, E, and A will all be higher. So the answer is B. Here's a question on maybe a driver's license exam. A car moving 50 kilometers per hour skids 15 meters with locked brakes. How far will the car skid with locked brakes if it is moving at 150 kilometers per hour? We could really get locked in with doing some a bunch of math with this, but I'm going to show you a quick way to solve that. Do it now.
Okay, so we're traveling 50 kilometers per hour. We hit the brakes. We skid 15 meters. If we're traveling 150 kilometers per hour, how far will our skid be? Well, first we got to look at this. My v squared is approximately the same as skidding distance. My velocity goes from 150 to 150, so I go 150 divided by 50, I get 3. 3 squared is 9. That means my distance will be 9 times. So 15 times 9, 135 meters. So if you triple your speed, your stopping distance increases by 9. That's why speeding, not the best option when you're driving.
2 baseballs are fired into a pile of hay. If one has twice the speed of the other, how much farther does the faster baseball penetrate? Assume that the force of the haystack on the baseballs is constant. So if one has twice the speed, all right, if you square 2, you get 4. So it will go, the faster one will go 4 times farther into the hay, because v squared equals d, like we talked about earlier. Quick way to do that one. Okay, so we got a roller coaster problem. Do it now.
All right, so roller coaster problem. At the beginning, you have 0 kinetic, 450,000 potential, height and velocity. Obviously, if there's no kinetic, you have no speed. So to find height, I take potential energy, and again, we got to find a mass. We'll say the mass of our cart is 100 kilograms. Again, just to make numbers easy. Normally that number would be given to you, probably be something harder than that. But potential energy, mass times G times H. Potential energy is 450,000. My mass is 100 kilograms. G is 9.8. Solve for H. 450,000. 100 times 9.8 and 2. 980 H. Divide both sides by 980. And my height of this roller coaster is 450,000 that's our height. So our height is 459. Now it gets down here and does a loop-the-loop. When it does a loop-the-loop, potential energy is 200,000. So if I take my total energy here minus 200,000, I get 250,000. And then when I do that, I should be able to continue on. So as I do that, I get 250,000 joules. And now I want to find height and velocity. So I got to solve for both. So here, potential energy, mgh, potential energy is 200,000 times my mass of 100 times 9.8 times h. 200,000, 980, that's just this times this, h, divided by 980, h. So 200,000 divided by 980, my height is 204 meters. And then what's my velocity? My velocity is, kinetic energy is 1/2 mv squared. My kinetic energy is 250,000. 1/2 times 100 times v squared. So 250,000. 1/2 of 100 is 50 v squared. Divide by 50. 250,000 divided by 50 is 5,000. Take the square root. That will give me v. So the square root of 5,000 is 70.7. So my velocity is 70.7 meters per second at that point. And then at the very bottom, my potential energy is 0. So my kinetic energy will be the full 450,000 joules. My height is 0. So therefore, I just got to find final velocity. And again, I use the equation 450,000 equals 1/2 times mass times v squared. 450,000 is 50 v squared. 450,000 divided by 50. 9,000 v squared square root. Square root of 9,000 gives me a velocity of 94.9. So my final velocity is 94.9 meters per second. Energy is conserved. Solve for everything else using potential and kinetic energy formulas.
We're looking at a ski jumper. We got Lee Benfartist, and he starts up here, and you can see all the numbers. But we want to find the speed at locations B, C, D, and E. Do it now.
All right, so ski jumper at different situations. I just wrote down kinetic energies of 20, 35, 20, and 50. And the mass, it said, is 50 kilograms. So our mass is 50. And we want to find the velocities. Again, kinetic energy, 1/2 mv squared. Kinetic energy of 20,000 is 1/2 50 v squared. 1/2 of 50 is 25 v squared. 20,000 divided by 25. I think I know it in my head, but I'm going to do it. It's 800 v squared, square root of each side. Square root of 800 is 28.2 meters per second. If my kinetic energy is 35,000, 1/2 50 v squared, 35,000, 25 v squared, divide both sides by 25. So 35,000 divided by 25, 1,400 v squared. Take the square root of 1,400. And my velocity is 37.4 meters per second. D, 20,000. same as B, so my velocity without having to do any work is 28.2. And then if I'm all the way down at the bottom and I'm traveling, the kinetic energy of 50,000 is 1/2 mass, 50 times V squared. 50,000 is equal to 25 V squared. 50,000 divided by 25 is 2,000 V squared, square root of 2,000. V is 44.7 meters per second, which should be faster than the others. That's how you solve those.